So next up we have Andres Prada, scientific specialist at the Illinois Sustainable Technology Center, presenting in person.
Okay, hello everybody here and online. So today I'm going to talk about how to entrap PFAS and destroy microplastics in biosolids. Okay, so biosolids come from wastewater treatment plants. So these plants receive in residential wastewater, industrial wastewater, and also landfill leachates. So from the 1990s, all landfills are required to collect the liquid waste, send it also to the wastewater treatment plants. So they treat all these kind of waste, and then the solid residue is what we know as biosolids. So these biosolids are very rich in nutrients and minerals. So they are a good soil amendment. So wastewater treatment plants can sell it as a organic soil conditioner, but it has also a lot of contaminants, including pathogens, PFAS, microplastics, heavy metals. So the wastewater treatment plants have to constantly be testing the quality of the biosolids to see if they are suitable for plant application or if they have to throw them in a landfill or even incinerate it. So we collected samples from 5 wastewater treatment plants in Illinois. So we collected inputs and outputs in each system. So inputs includes landfill leaching, city sewage, and for outputs we have the wastewater effluent and biosolids. And we analyze it for PFAS and microplastics. I'm not getting into the detail of all the PFAS compounds, but I'm giving just an overall average of all the PFAS. I mean, there is all kind of PFAS in this wastewater. So in general, we found in the landfill leachate like 1,000 parts per trillion of PFAS. Then in the city sewage, 100 parts per billion. Now it passed the treatment, and we find the same concentrations in the effluent, 100 parts per trillion, and then 1,000 parts per trillion in the biosolids. Now for microplastics, the concentrations are in parts per billion. So we found 10 parts per billion in the landfill leachate, 100 parts per billion in the city sewage. Then it goes down in the effluent to 1 part per billion. And then the rest of them is concentrated in the biosolids, where we found like thousands parts per billion there. So this is consistent with other studies. There's a lot of papers that have reported that 99% of the microplastics go to the biosolids. And PFAS are chemicals that attach very easily to any surface. So they can attach also easily to organic matter. So that's why we find a lot of them in the biosolids as well. So if we land apply these biosolids like that, they also dissolve very easily with water. So they will eventually mix with rainfall and mix with the runoff or percolate through the groundwater system. So there are some treatments for biosolids, such as the hydrothermal treatment or thermal desorption, but they require specialized equipment and a lot of energy. So that might not be cost effective if we want to treat large amounts of biosolids. But one alternative solution is to convert those biosolids into biochar. So biochar is made from biomass, so leaves and sawdust, and that can be pyrolyzed and produce biochar, bio-oil, and syngas. So talking about the biochar also has the nutrients and all the soil conditioner properties to be sold as an organic fertilizer. but it also has other environmental benefits. So when we pyrolyze the biomass, we are sequestrating the carbon that it's in the biomass, that naturally it will be released as CO2, but we are carbonizing that biomass and sequestrating the carbon, putting it in the soil where it will stay for hundreds of years. So it's also, biochar is also a mitigation strategy for climate change. So if we mix the biomass with the biosolids, we can produce a biosolids-based biochar. So, but our approach was to reduce the temperature that pyrolysis needs to carbonize the biosolids and the biomass. So usually pyrolysis, it's run at temperatures of 900 or even 1,000 degrees Celsius, but we lower the temperature up to 450 Celsius, so that we can reduce a lot the cost of this process, but at the same time, we guarantee that we are converting it, we are carbonizing the components. So this is different from incineration. Incineration of any material containing PFAS has been banned by the Department of Energy, of Defense. So when we incinerate any material with PFAS, we are destroying the PFAS, but those components evaporate and they become a hazardous, volatile PFAS components. So with our low temperature pyrolysis, we want to avoid the destruction of PFAS and the generation of volatile components, toxic components. So what is happening in our low temperature pyrolysis is during the carbonization, we are entrapping the PFAS there in the char. And at the same time, we are carbonizing microplastics, and we are killing all the pathogens. So around 450 Celsius, it's a good temperature to obtain that. So now we tested in the lab our biosolids-based biochar compared to the raw biosolids. So we rinse it several times. So in the orange line, we see that there is no PFOA leaching from the biochar, whereas the biosolids, with every rinse, it's releasing more and more of the PFAS. Now this is very preliminary results, but we put some big pieces of plastic, and we see that we couldn't find those pieces because they were carbonized. So in summary, so wastewater treatment plants have a good product in the biosolids. However, it needs to be treated before a safe land application. So, and cost-effective way that we are proposing is to create biochar from those biosolids. And as I said, we are not destroying the PFAS, but we are encapturing the PFAS and trapping the PFAS in the char. We are carbonizing the microplastics as well, and then we are killing all pathogens. Well, at the same time, we preserve the nutrients and minerals. So it can be also sold as a soil amendment. So I want to acknowledge my supervisors, Waysign, John Scott, Lee Green for the analytical work, the Hazardous Waste Research Fund, and Beth for providing us the fund for the sampling and analysis, and all the hourly students that help us. So I can take any questions.
Have you looked at, I'm sure you've looked at scaling this up from your lab?
Yeah, I mean, the charcoal industry is like well developed. So they have the reactors and everything that we can use also to produce the biosolids-based biochar. So it's feasible to scale it up.
Have you petitioned anybody to try it? Or?
Yeah, I mean, we were partnering with the Chicago Sanitary District. We submitted a proposal. I mean, we are trying to get more funding to test it larger scale. Yeah, so we are in the process. We have the preliminary results to submit proposals for more money and scale it up, do more testing. But yeah, this is all lab scale for now. Yeah.
Nice job. I have two questions. The first is, have you ever characterized the biochar you made? I want to know the porosity and the density of the biochar. Have you done that before?
Yeah, I don't know. Do you know Wei? Here in my supervisor Wei, he knows more. Thank you, Wei.
For the density, because this, if you biochar made for the biomass, usually very light material, but the biochar made from the biosolids, because biosolids have a higher ash content. So this density usually is high. I think that you can say 1.3, 1.4, kind of like soil.
And another question is, I know biochar is a new material, but when you use different biomass, different material, for example, from bamboo to carton or some other thing to make the biochar is different a lot. Do you have any idea which kind of material is better?
Yeah, that's a good question. And that's something that needs more research. So we want to mix the biosolids with biomass to increase the amount of carbon that is there. So biosolids by itself has low carbon compared to a biomass. So we mix it to make more carbon material. So in terms of climate change mitigation, we want to sequestrate as much carbon as we want. So to answer your question, which is the best material, I would say the one that has more carbon, so we can sequestrate more carbon and put it in the soil.
Thank you.
Thank you, everybody.